For the last portion of 11.1 sequences, we have a theorem called the squeeze theorem. And the squeeze theorem says that if we had three sequences, a sub n, b sub n, and c sub n, and at some point a sub n was always less than or equal to b sub n, which was less than or equal to c sub n. So what we're actually saying here is that b sub n is squeezed between two other sequences. So it's squeezed in between a sub n and c sub n. So if we can actually squeeze b sub n, and I know the picture's a little fuzzy here, but if b sub n is the sequence that gets squeezed in between two other sequences, and we know that those two other sequences have the same limit, then we have to know that the sequence that is smashed between, squeezed between, has to have that limit as well. And this is a useful theorem that we can apply when we're not sure what's happening exactly to our sequence, but we know that it is in between two sequences whose limits we do know. So let's look at a couple examples of this one. And then get into some growth rates of sequences which utilize squeeze theorem. So let's take a look at this first example. I have a couple examples here, and I think I want to just talk about the first one, and then the second one we can talk about with growth rates of sequences, or we could actually do that using the squeeze theorem in one of our class sessions. So let's take a look at this first one. So if this first one, and I'm going to take it over here, this first example, if we were to think about the sequence, and it was 2 inverse tangent of n over n cubed plus 1. And I were to want to think about what is this squeezed between? How does this compare to two other sequences? And what I want to talk about, and the reason I grabbed this inverse tan, we could just as easily have put a sine or a cosine here as well, because both, or all three actually, let's make a note, whenever we're using comparisons or using a squeeze theorem and we end up seeing an inverse tan or a sine or a cosine, note that these are all bounded. So let's make a note, some bounded functions that come up and can be utilized when we're talking about a squeeze theorem or a comparison theorem or something of that form. So for instance, this particular one, the inverse tangent, we know is bounded between pi over 2. It has horizontal asymptotes at pi over 2 and negative pi over 2. So we know that, and we can utilize that. We'll go back and use a squeeze theorem with that fact in just a second. But I wanted to mention we also know that the sine of x is bounded. The sine of x is between 1 and negative 1, and the cosine of x is between 1 and negative 1. So these are just some useful, let's give them a little bubble, maybe even some fireworks, because why not? They are useful enough to remember. And as we move forward through this chapter, those are going to come in handy when we do comparisons, when we do squeeze theorems, anything of that form, remembering what functions we know are bounded, that when they pop up, we can almost think about like, well, the sine never gets bigger than 1, or the inverse tangent never gets bigger than pi over 2. So it's this bounded function. We can utilize that. Okay, so let's come back. So how do we use a bounded function and the squeeze theorem here? So what we can do here is we can say, well, 2 inverse tangent of n, let's set up that inequality. 2 inverse tangent of n, well, we know that that is got to be less than 2 times pi over 2, because the inverse tangent has to be less than pi over 2. We also know that it has to be greater than 2 times negative pi over 2. So we know that it's bounded on either side. So if we just simplify that a little bit, this is just negative pi is less than 2 inverse tangent of n, and that has to be less than pi. So we know that 2 inverse tangent, the numerator of our sequence, has to be bounded by those two constants, negative pi and positive pi. We also know that n cubed plus 1 is always positive if n is greater than 1. So we can actually now come in here and divide everything by n cubed to create that sequence, and two other sequences that it is bounded by. So we can go ahead and put those just like that. Now, I will make a little note. I did that in red, and let's make a note here. This is since we can do that without flipping the inequality, since n cubed plus 1. And it is a cube, so we'd have to be careful of that. But the index starts at 1 and goes to infinity. So we know that this is greater than 0. So it won't change my inequalities. So if I know all of that, then I can absolutely take a look at these two pieces and just say, well, each of those two pieces, where the limit as n approaches infinity of negative pi over n cubed plus 1 equals 0, and the limit as n approaches infinity of pi over n cubed plus 1 has to equal 0. So therefore, these are my 3 dots for the therefore, we must know that by the squeeze theorem, that our sequence, the sequence of 2 inverse tangent of n over n cubed plus 1, must also converge to 0. Okay? And we could just as easily have replaced, in that sequence, we could just as easily have replaced this inverse tangent of n. Oops, sorry about that. I actually meant to do a highlighter. This inverse tangent of n, we could just as easily have replaced that with a sine of x or sine of n or a cosine of n, and then that also would have been bounded by something different, negative 1 and 1 instead of pi over 2 and negative pi over 2, but we could have followed that through with the squeeze theorem as well. So the squeeze theorem can be useful for our purposes when we have a bounded sequence. We can show that the bounded sequence, if we have a bounded sequence and the sequences on either side approach the same limit, we can show that that forces the sequence in the middle to converge as well to that same limit. So there's an example utilizing the squeeze theorem. I also want to talk about one other useful fact that comes up in this sequence section, and that is the growth rates of sequences. Now this growth rate of sequences chart and formulas is not actually given in the Stewart textbook. It was utilized in a textbook that we used to use previously, and I think it's fairly useful that I wanted to capture it here. I put it into the Canvas course as well, this actual chart. So this growth rate of sequences says that we know certain sequences grow faster than other sequences. So, for instance, an exponential is going to grow faster than a polynomial. We do know that at this point in our mathematical career. Our mathematical sophistication should tell us that exponentials grow faster than polynomials. Exponentials grow faster than most functions. So, or most sequences, most functions, most sequences. And so, if we're comparing two sequences and we happen to have them in a ratio a sub n over b sub n, and we know one of them grows faster than the other, that can be very useful for us when we're looking for the limit. And so that's what this growth rate of sequences says. It gives us a list. It says the following sequences are ordered according to their growth rates in increasing growth rates. So these are ordered by increasing growth rates, so that if a sub n appears before b sub n in the list, and we're taking the ratio of a sub n over b sub n. So if we look at a ratio where we know the sequence on top is growing slower than the sequence on the bottom, another way to say that, the sequence in the denominator is growing faster, then this has to go to 0. And if we flipped that ratio and we put the sequence that's growing faster in the numerator, well, then that limit would have to approach infinity. Okay? And so these little double inequalities here are saying that these growth rates, these are comparing the growth rates of these particular sequences. And so you can see as we go along, you've got your logarithms, you've got your polynomials, you've got your polynomial times a logarithm, you've got a polynomial to a higher power, then you've got exponential, a base raised to a power, then you have your actual factorials, and then you have a power of index raised to a power, n to the n, is being the fastest growing growth rate. So we can utilize this, and you are welcome to reference your growth rate of sequences when you're computing these. And I want to just show you how this would work out, both using the growth rate of sequences, but also just using sort of what we know about how these sequences grow. So I want to show it in both ways here, kind of explain where this growth rate of sequences is coming from numerically when we actually have a particular sequence, but then also reference it when we're looking at it. So again, I'm going to just grab one of my examples, and we can do more examples in the class session, or if you have individual questions, we can do more examples off of the worksheets. So let's grab this example that I have highlighted, n factorial over 5 to the n, from n equals 1 to infinity. And let's talk about, does that sequence converge or diverge? So let's come over here and let's take a look at that one. So it was n factorial over 5 to the n, and let's n equals 1 to infinity. So let's take that from n equals 1 to infinity, and let's go ahead and consider what is happening to that actual sequence. Because if we were to just want to take the limit as n approaches infinity, if we were to try to just take the limit of this, limit as n approaches infinity of n factorial over 5 to the n, we end up knowing that the numerator is growing without bound, but so is the denominator. So we end up with that indeterminate form, and this is where we have to actually think about, well, which of those is actually increasing at a faster rate than the other. And we can reference those growth rates, and I'll go back to that in just a second, but I want to explain where that comes from, how we can see that n factorial is actually going to be growing faster than 5 to the n, that exponential on the bottom, because these are both very fast growing sequences, n factorial and 5 to the n. So when we take their ratio, it can be sometimes difficult to just see which one is growing the fastest. And so we do have infinity over infinity, and you might think, I'm just going to apply L'Hopital's rule, which would be fine for the denominator, but we don't know how to take the derivative of n factorial. So we can't actually apply L'Hopital's rule here in order to take this limit. So we have to do some other strategy. So let's consider here for a second just n factorial. What does n factorial actually represent? What does 5 to the n represent? So let's make a little note here, and let's think about, well, what does this represent? And I will say this, that this is always greater than 0. These are always positive, so we can start with that on the left-hand side. And then we can start expanding. So n factorial, if I expand n factorial out, if I actually write that out, and I can start with n times n minus 1, there's multiple ways to write factorials. I'm going to start with 1 times 2 times 3 times 4 times 5, and I'm going to go out just a little ways because I want to really illustrate this point, times all the way out times n minus 1 times n for the factorial. So whatever the index is, whatever term we're looking at, if we were looking at the millionth term, then we would be 1, 2, 3, 4, 5, 6, 7, all the way out to a million. Okay, so divided by, and on the bottom we've got n fives. And if you notice, if we were to look at just the first term, so just the first term would give me just 1/5. And if I had just 1/5, that looks like the numerator is smaller than the denominator. And then I would have the second term, so I would multiply by 2/5. So then I'd have 2 over 25. Still looks like the numerator is smaller. Then I would have 3. Then I'd be multiplying by 3 over 5, which would give me in the numerator 6 over 125. And then I would have 24 over 625. And it's looking like this is actually, the numerator is actually smaller here for a second. But notice what's happening. Then the 5s cancel. Then the next term I'd just be multiplying by 1. And take a look at what happens for each of these following terms. I'm going to be multiplying by a ratio for everything now from here until the end, until n gets to infinity. I'm going to be multiplying by a ratio that is actually greater than 1. Each of these terms that I'm multiplying by is going to be greater than 1. Now I'm going to leave this last term here because I want to leave that n over 5 there for our purposes on the next line. So let's leave that n over 5 there. But notice that this entire product that I have right here, I'll highlight it, this whole product right here, when I multiply quantities like 6/5 times 7/5 times 8/5 times all the way out to n minus 1/5, when I multiply those are all greater than 1, which means that their product has to be greater than, this is going to give me a number that is greater than 1. So when I go to my next line and I say, okay, so this is n factorial over 5 to the n, and we know that that is actually going to have to be less than, now notice what I have here. I have 1 times 2 times 3 times 4, so that is actually 24 over 625. 625. So that's just a constant. I'm just going to leave it like that, 24 over 625. And then I'm multiplying by some number that has to be greater than 1. Okay, so that means that I know that this sequence that I'm looking at has to be greater than 24 over 625 times 1 times, and I'm going to leave that n over 5. Okay? I left that n over 5. I need that n over 5 so that I can talk about what's happening to the sequence. So I left the last factor in our expansion there. Okay? I could have dropped it and I could have just said we know that this thing is greater than 24 over 625, but I need that n over 5 so that I can show what happens as n approaches infinity. So notice right here what's actually going to happen. What's going to happen here is we're going to have a sequence n factorial over 5 to the n, and we know that that has to be greater than, oops, guys, I'm sorry, I made a mistake up here. This should have been greater than, and I'm going to need to drop my, I know my sequence is greater than 0, but I need to drop that inequality from up above. This sequence is actually greater than 24 over 625 times 1 times n over 5. So I made a little mistake right there, guys. Make sure if you're following along here with this video, I made a mistake here. This is definitely, our sequence is definitely greater than 24 over 625 times 1. And I am going to erase the other end of it. It is also greater than 0. We know it's positive. Okay, so this ends up being 24 times n over 3,125, just multiplying out the 625 times 5. So we do have that denominator, and it is kind of large. And for the first bit of terms, for the first bit of these terms, it might not appear as though they are growing or growing without bound. But look at what's going to happen now. If I consider what happens right here to this limit, so think about this sequence right here. If I take the limit as n approaches infinity, which is what we're doing, we're letting n go to infinity, grow without bound, 24 times n over 3,125. This has to approach infinity. And we're saying here that our sequence is actually greater than something that approaches infinity as we go to infinity. So what this tells me right here is that we must have a sequence here, that the limit as n approaches infinity of n factorial over 5 to the n must also approach infinity. It has to approach infinity. The numerator, another way to say that is that the numerator, n factorial, grows at a faster rate. It takes a little bit, but it does grow at a faster rate than 5 to the n, the denominator. The numerator grows at a faster rate than the denominator. And if we go back to what we had mentioned at the beginning of this example, when we were looking at growth rates of sequences, if we look at the growth rates of sequences here, and we look at the comparison of n factorial, if we actually look at these growth rates of sequences, here's our n factorial, and here's our exponential. So here is the 5 to the n, and here is the n factorial. So if we had been utilizing just the growth rate of sequences, we could see, I just wanted to show why that is. Why is n factorial grow at a faster rate? And so I wanted to show you guys that by actually looking at that inequality. But we could have actually done this example. So another way to set this problem up, if I was asked to compute the limit or find out if this converges or diverges, another way to do this particular problem would be to actually utilize the growth rate of sequences. So we could say, here's another way. Use growth rate of sequences. And if we use the growth rate of sequences and we look at n factorial over 5 to the n, what we can say here is that this has to diverge to infinity by the growth rate of sequences, and we have to talk about the comparison of the numerator to the denominator. So by growth rate of sequences, and what we would say here is that 5 to the n. We know by the growth rate of sequences that an exponential, I'll pull that back up again, that an exponential grows at a slower rate than a factorial. So we can go ahead and utilize that. We can say 5 to the n has a growth rate smaller than n factorial. So this must diverge. Since n factorial is in the numerator, this must diverge. Therefore, the limit as n approaches infinity, since n factorial is in the numerator, this has to approach infinity. So that is another way to show what we showed up above, just utilizing those actual growth rates of sequences. So if you find growth rates of sequences to be helpful for you, then please do utilize that. And you can use that to show these limits based on which of the sequences is in the numerator and which is in the denominator.